Hey there, and welcome. Have you ever stopped to think about how a voice call or an email or even this whole thing reaches you from literally anywhere on the planet instantly? It sounds impossibly complicated, right? Well, today we're going to pull back the curtain and uncover the surprisingly simple blueprints that actually run it all. So, let's get right into it.
Okay, so let's start with a big question. How does any message, I'm talking a text, a song, a video stream, get from its starting point, point A, to its destination, point B, in what feels like the blink of an eye?
You know, believe it or not, the answer has a ton in common with something we all get, the good old postal service. Just think about it for a second. First, you write a letter, that's your source. Then you put it in an envelope and address it, that's the transmitter's job. It travels in a mail truck, dealing with roads and traffic, that's the channel. The person on the other end opens it up, that's the receiver. And finally, they read your message, the destination. This simple 5-step idea is the secret key to everything we're about to talk about.
So here's what we're going to cover. First, we'll break down that universal journey that all information takes. Then, we'll see how that journey powers the entire internet using light itself. And finally, we'll look at the actual electronic toolkit engineers use to build and test all these systems. See? It's all connected. Let's jump in.
All right, section 1. Let's take that postal service idea and turn it into the real 5-step blueprint that applies to pretty much every communication system ever made.
So it all starts with the source. That's what creates the original message, maybe your voice in a phone call. The thing is, your voice can't just travel through a wire by itself. That's where the transmitter comes in. Its job is to take that message and package it for the trip. And a huge part of that packaging is this really clever technique called modulation, which kind of gives our signal superpowers for its long journey.
So, what is modulation, really? Well, think of it like this. Most raw information, like the sound of my voice, is low frequency. That's okay for short distances, but it's like sending a letter by bicycle. It's not going to get very far, very fast. Modulation is the trick of piggybacking that low-frequency message onto a much higher frequency wave. It's like taking your bicycle letter and putting it on a supersonic jet.
So once our signal is modulated and ready for that supersonic trip, it enters the channel. This is just the physical path it takes. It could be a copper wire, a strand of fiber optic cable thinner than your hair, or even just the air for things like Wi-Fi or the radio. But, no channel is perfect. They all introduce one major headache. And that headache is noise. Noise is basically any junk that gets mixed in with our original message. In our postal analogy, noise is the traffic jam, the bad weather, maybe a smudged address, anything that makes the delivery harder. In our world, it's the static on a radio or the fuzzy pixels in a bad video stream. It's the enemy of a clear signal. So finally, way over on the other end, we have the receiver. Its whole job is to catch that incoming signal, noise and all, and then just reverse everything the transmitter did. It filters out as much noise as possible and performs demodulation to pull out the original message. And then, that clean signal gets handed off to the destination, the speaker that plays the music or the screen that shows the picture.
Okay, so we've got this universal blueprint. Now let's really put it to the test. In this next part, we're going to see how these exact same 5 steps are at the very heart of the technology that runs our entire internet, communicating with pure light.
So how in the world do you package a message into a beam of light? It's actually pretty wild. The transmitter takes our regular electrical data and uses it to flash a tiny, powerful laser. And this thing doesn't just turn on and off. It blinks millions, even billions of times a second, encoding our data into these little pulses of light. Then, a tiny lens focuses that flashing beam perfectly into a strand of glass.
And on the other end, it's just as cool. A lens directs those light pulses onto a special light detector. And this little sensor does the exact opposite of the laser. Every time a pulse of light hits it, it creates a little pulse of electricity. These electrical pulses are then put back together, perfectly recreating the original message. From electricity to light and back again, it's just amazing. And this is why fiber is so fast and is almost totally immune to that noise we were talking about earlier.
Okay, so we've seen how these amazing communication systems work, from a simple letter all the way to a beam of light. But that brings up another question, right? How do engineers actually design, build, and fix this stuff? How do they even work with these invisible signals in the first place? Well, for that, we need to open up the electronic toolkit.
And to answer that, we've got to dive into the world of electronic test instruments. And guess what? Just like our communication system, most of these instruments follow another simple 3-part blueprint. First, a transducer turns some physical thing into an electrical signal.
Then a signal conditioner cleans it up and gets it ready. And finally, an indicating device, like a screen, shows you the result. Think of a digital thermostat. A sensor measures the heat, a chip processes it, and the screen shows you the temperature. Simple, right?
So let's zoom in on two of the most essential tools you would find on literally any electronics lab bench, because they perfectly show this blueprint in action.
Meet the workhorses, the digital multimeter, or DMM, and the function generator. They're really like two sides of the same coin. The DMM is your ultimate measuring tool. It tells you what's going on. The function generator is the ultimate creation tool. It lets you make exactly the signal you need.
And the DMM follows that instrument blueprint to a T. First, its probes take in the raw electrical signal. Then, this signal conditioning stage preps it, scaling it up or down to get it in the perfect range. Then the real magic happens. An analog-to-digital converter turns that smooth real-world signal into a number. And finally, that number pops up on the display. It's a measurement machine. The function generator, on the other hand, is all about creation. Its entire job is to generate clean, perfect, repeating electronic waveforms whenever you want. With just the turn of a dial, you can get a smooth sine wave, a sharp square wave, or a straight triangular wave. And you have total control over their amplitude, that's how tall they are, and their frequency, how fast they repeat.
So as we start to wrap this up, what's the big picture here? Well, the main takeaway is that all of this incredibly complex technology, from the internet to the tools we use to build it, is based on simple, repeatable blueprints. It's all just building blocks.
I mean, we started with a simple postal service analogy, right? And we saw those exact same ideas, creating a message, packaging it for a channel, and receiving it on the other side, play out in a super high-tech fiber optic system. We even saw a similar input-process-output logic in the lab tools we use every day. It's all the same core principles.
These blueprints, these fundamental rules of how to create, send, and measure information, they are truly the foundation of our modern connected world. They're elegant, they're powerful, and they're surprisingly simple. Which really just leaves us with one last thought. What incredible new things are we going to build with these same building blocks next? Thanks so much for watching.